Okay, this question says, discuss the continuity of the function. State the interval where the function is continuous and whether the discontinuities are removable or non-removable. So in this example, we have f of x equals x squared minus 9 over x squared minus x minus 6. So for this type of function is a rational function. And we know, based on it being a rational function, that if we find the domain, we're going to be able to find the intervals where this function is continuous. So we know that from a theorem we have related to this. So what we want to do is figure out the domain of this function, x squared minus 9 over x squared minus x minus 6. So if I factor the denominator, and I'll go ahead and factor the numerator at the same time, we have x plus 3 times x minus 3 for the numerator because that's a difference of squares. And for the denominator, we have x and x. 3 times 2 is 6, a negative 3, and a positive 2. So when we're finding domain of rational functions, we find the domain by setting the denominator equal to 0. So if I set my factors from the denominator equal to 0, that's going to give me the values to exclude from the domain, and it's also going to give me the discontinuities. These are going to be our discontinuities. So now, based on just this, I know that I have discontinuities at 3 and at negative 2. So thinking about that on the number line, in order, I've got negative 2 and 3. These are going to be the discontinuities. Everything else is going to be continuous. So that's going to be negative infinity to negative 2, negative 2 to 3, and 3 to infinity. So the function will be continuous on the domain, which is what I have listed here. But then to know what type of discontinuities we have, whether they're removable or non-removable, depends on whether these discontinuities are vertical asymptotes or holes in the graph. So to tell the difference between whether the function has a vertical asymptote or hole, that's why we look at the numerator. So you're looking for common factors. If you have a common factor, like we do here, of x minus 3, that's what creates a hole in the graph. That's what's going to create, if you were to find the limit at that point, that's what creates the 0 over 0. And then you would cancel that out, and then you would end up getting a number for the limit. So that limit's going to exist, and that creates the hole in the graph. And we saw that a hole in the graph is a removable discontinuity. So this is where we have a hole, and that's a removable discontinuity. Now we look at the other factor of x plus 2, and there's no common factor. So at that point, that's going to create a vertical asymptote. And the vertical asymptote is a gap in the graph that's bigger than a single point, so that's going to be non-removable. So we've got the smaller discontinuity, that's negative 2, and that would be non-removable. And then the larger discontinuity is at 3, and that one's removable. This question says use the alternative form of the derivative to find the derivative at x equals c if it exists. The alternative form of the derivative is this here. F prime at c, the derivative at c, is the limit as x approaches c of f of x minus f of c over x minus c. So this is the derivative at a particular point. And for this example, we have our function f of x equals x minus 6 to the 2/3, and the value of c being 6. So to calculate the derivative at the value of 6, we're going to use this alternative form, which is the limit as x approaches 6 of f of x minus f of 6 over x minus 6. So far, all I've done is replace the value of c with 6. And now we're going to simplify this limit. So starting with f of x, I'm going to replace f of x with the given function. We have the limit as x approaches 6 of x minus 6 to the 2/3. Then we need to subtract f of 6. So let's calculate f of 6. F of 6 is 6 minus 6 to the 2/3 power. 6 minus 6 is 0, and 0 to the 2/3 power is 0. So f of 6 is 0. And then we've got divided by x minus 6. I'm going to continue to simplify this limit. And x minus 6 to the 2/3 power minus 0 will be x minus 6 to the 2/3. If I try to calculate this limit right now, I would get, with direct substitution, I would get 6 minus 6 to the 2/3 over 6 minus 6. And this is going to give me 0 over 0, an indeterminate form. But that indeterminate form tells me there might be some simplification that I can do on this function, on this expression. So I notice that x minus 6 is a factor in the numerator and x minus 6 is a factor in the denominator. So I can think of this as x minus 6 to the 2/3 over x minus 6 to the 1st power. And since they have the same base, I can combine their numerators. So this is going to be the limit as x approaches 6 of x minus 6 to the 2/3 minus 1. That's the limit as x approaches 6 of x minus 6 to the 2/3 minus 3 over 3, which is the limit as x approaches 6 of x minus 6 to the negative 1/3 power. So then if I rewrite this, that would be the limit as x approaches 6, and we've got a negative in the exponent. So that means I can write this with the reciprocal of 1 over x minus 6 to the 1/3 power. And we know we have a theorem that says if I do direct substitution and I get a non-zero over 0, then that means that this graph has a vertical asymptote at that value. And that's exactly what happens here if we substitute the 6 in. We get 1 over x minus 6 minus 6 to the 1/3 power and that's 1 over 0 to the 1/3 power. So we have this situation where we have a non-zero over 0, and we have a vertical asymptote. So because of the vertical asymptote, I know that this limit does not exist, and since the limit does not exist, the derivative does not exist at that value. Okay, so we've seen that the derivative does not exist at the point x equals 6. So let's see what that looks like graphically and why the derivative would not exist at that value. So what I want to do is type in my function into the y equals menu, and my function is x minus 6 to the 2/3 power. Let's take a look at the graph. And I'm going to show you on the graph where x equals 6 with the cursor by hitting second calc, number 1 value. I'm saying a value of 6. So now you can see my cursor blinking at that value of x equals 6. And what we have at that point is something called a cusp. And if you keep in mind what the derivative stands for, the derivative stands for the slope of the tangent line. And let me go ahead and kind of give a sketch of that picture over here. We have a cusp that looks like this. So as you trace the graph coming from one side, we would be getting to a tangent line that maybe looks something like this, that looks like it has a negative slope. However, when we trace the tangent line coming from the other side, or trace the graph coming from the other side, our tangent line would look something like this, and that tangent line has a positive slope. So we have on both sides the tangent line not agreeing with each other. And so because of that, the derivative doesn't exist at that value. The same thing happens with absolute value functions. They have, instead of a cusp, it comes to a corner. And so on one side, you get the tangent line being negative, and on the other side, the tangent line being positive. And so when you get to that corner, it doesn't agree on both sides. And so the derivative doesn't exist, and the slope of the tangent line doesn't exist.